example number 5. Determine the set of points at which a function is continuous. So first, let's start off by finding the domain D of f. Alright, so in the inside we see that 1 plus x minus y has to be greater or equal to 0 because it's a square root function, which means x minus y has to be greater or equal to -1 for all x, y. So that means that the domain D for this function is a set of ordered pairs x, y such that x minus y is greater or equal to -1, where x and y are real numbers. Now this function here is actually continuous on its domain D for all these points because cosine is a continuous function and the square root function is continuous, and we have a composition of two continuous functions on their domain D, so f is continuous. So we know that f is continuous on D. For h, it's a slightly different story. So if we let x be 0 or we let y be 0, we get e to the 0 in the denominator. E to the 0 minus 1 is 1 minus 1, which is 0. So we know that there's going to be a discontinuity at any pair points where you have 0 comma y or x comma 0. Okay, so it's discontinuous at these points here, and really that's the only two numbers where x, y can be equal to 0 is that x is 0 or y is 0. So you know that their discontinuities will be here. So in particular, one discontinuity would be at 0, 0, right? So we could say that h is continuous for all points on its domain all points on its domain, but that domain D in this case is different. We have it's an ordered pair such that x comma y or 0 comma x comma 0 comma y, where x and y are real numbers, are not included. And if you think about that, that would be just the axes, right? Here, x-axes are not included, and this would be the y-axis is not included. So really, we're not including the axes in the domain of h. So h is continuous for all these points, which exclude these discontinuities. All right. So it's a little bit of a point there. All right, let's go on to example 6 and discuss continuity. So here we have a piecewise defined function, sine of xy over xy if xy is not 0, and 1 if xy is 0. Now think about continuity in general at a point. Okay, so in the previous example we were talking about continuity of the function in general on a domain, right? But here we're talking a particular point, namely when xy is 0, right, for any of those pairs x comma y that satisfy this, right? We have to consider the definition of continuity. So we're really trying to think of, okay, what makes this, first of all, what makes this sine of xy over xy undefined, right? So what makes sine of xy over xy undefined? That's when x or y is 0, or x times y is 0, which implies that x could be 0 or y could be 0. Now, the first part is defined for when x and y is not 0. So actually, this first part, sine of xy over xy, is actually continuous on its domain, which excludes the points x times y does not equal 0. Okay, so that's kind of, that's kind of the point here, is that this is continuous on its domain given this condition here. Okay, now if we do compute like f of let's say 0, 0, okay, that will have to be equal. This is just using the limit definition of continuity goes to 0, 0. Say if we're looking at 0, 0, of course the first one will not be defined at 0, 0, but in the limit we could take the limit of this, okay? And really f of 0, 0 on the one hand is 1 because we know that x times y would be 0 there, so we know that that's 1. And on the other hand, we have to see if this limit is also equal to 1. Now this should remind you of something that you learned in Calculus 1, namely that the limit as x approaches 0 of sine of x over x is 1. Okay, and this is basically the same concept here. So that's why we can use this limit to say that this limit is just 1. Okay, so it's the same thing as replacing, basically letting the limit as t goes to 0 of sine of t over t, where you let t be xy, and kind of play around with this limit to get that this is also 1. So that means that this function here, f of xy, is continuous at 0, 0. Now what about if one of the two are 0, say if x is 0 or y is 0, right? Well, if x is 0 or y is 0, then you'll be, in this case here, and it'll still be 1 over here. If x is 0 or y is 0, you'll still get 1 on this side. So I'm looking at the case where, let's just do x, for example, where 1 is equal to f of x comma 0. That's still in the second case, right? And we have to see if is that equal to this limit. And if it is, then we know it's continuous there. Sine of xy over xy. And we know that this is the same thing as the argument for f of 0, 0. So this would be also 1. Okay. So regardless if both are 0, one of the two are 0, your limit is still going to be 1 over here, which means that f of xy is continuous. And when you say that, it means that it's continuous on all points everywhere on its domain. So its domain is all real numbers, and it's continuous for all real numbers, all real ordered pairs that consist of real numbers. So yeah, this is using this fact here, which basically you could think of this going back to Calc 1. You could think of this as like proving this limit using the L'Hopital's rule, or showing that this is 1 using the L'Hopital's rule. Is one way to show this. But in any case, we see that this is continuous on its domain. Let's jump into a little bit of partial derivatives. So computing partial derivatives using definition and other methods, implicit differentiation, Clairaut's theorem, PDE's Laplace equation and harmonic functions, and applications to partial derivatives. So these are just some of the things that we need to look at in this section of the partial derivatives in your book. So let's compute some first partial derivatives, and I'll explain a little bit here how to do that. So the notation we're going to use is this curly D notation. This means partial derivative with respect to x of f. So that's going to be equal to, now what you do for partial differentiation is a bit different than regular differentiation, is you hold the other variable as a constant and then you take the derivative of this variable. So in the first one it would be 2xy because we're holding y as constant and taking the derivative of x squared. And then if I take the derivative of minus 3y4 to respect to x, that's just 0. So df dx is just 2xy. Now let's do df dy. It's the same thing, except we hold the x constant. So we have x squared minus 12y cubed. So that would be df dy. That's the first partial derivatives that we just computed. Now, sometimes people write this in a little notation as fx, and sometimes people write this as fy for short. You'll see this notation used pretty much everywhere. It's just more convenient. So if you have to compute second partial derivatives, let's say if you did the second partial derivative with respect to x, you do the same process and you just get 2y. Let's say if you had to do it with respect to y on this one, you get negative 36y squared. And you could also take what they call mixed partial derivatives. So if you do f of xy, that means first take the derivative with respect to x, then take the derivative with respect to y. So you'd look at this one here, take the derivative with respect to y, and you just get 2x. Conversely, you could take the derivative with respect to y first, then with respect to x, and then you get just this would be just 2x here. So yeah, you see the first partial derivative with respect to y is this, and then you're taking the partial derivative with respect to x here, so you just get 2x here. So actually in this case we do see that fxy is equal to fyx, and that's a special property of this particular function and a property that we will investigate in a little bit, where the mixed partial derivatives are the same value. Let's look at B. B is we're trying to do du partial with respect to u, partial with respect to r. So let's take a look at that. So we have a composition of two functions. We hold theta to be constant in this case, okay? And we have to use the chain rule here to do this, okay? So let's take a look at that. Derivative of sine is, of course, cosine of r cos theta. And then you have to times it by the derivative of r cos theta, but we're holding cos theta to be a constant, so we just get cos theta. All right, and we could do the partial with respect to theta now. Compare those. So we're going to be holding r constant in this case, so we're going to get cosine r cosine theta once again times a derivative with respect to theta is negative sine, so you get r times negative sine theta, so you get negative r cosine theta sine theta. And sorry, I ran out of room there, but that's what you get. So that would be the first partials of this particular function. If you want to put it in the same notation as before, it would be ur, and this would be u theta. So yeah, you can take a first partial derivatives, second partials, and what they call mixed partial derivatives too. All right, let's jump into another example here where we're going to be using a little bit more of the definition to talk about taking the partial derivative. And by the way, everything that we're doing here can easily be extended out to 3 variables, okay? So there's not too much difference in what we're doing here, except you have x, y, and z perhaps as your input. You have a triple instead of an ordered pair, but basically all the computations are more or less the same. Let's look at example 8. Use the definition of partial derivative as limits to find partial with respect to x and the partial with respect to y. So using the limit definition is a bit different than just computing it using our normal methods that we're aware of. So we should first state what that would be, right, in terms of our limit definition. So let's state our limit definition for taking the partial with respect to x. Okay, so here it is. So now we're just going to begin working with this limit definition. And it's similar to calculus 1, but here we have a function of 2 variable. Okay, so just have to make sure that we keep track of everything, all the variables here. And plug this in. Now here we see that we need common denominator, and the LCD would be x plus y squared times x plus h plus y squared. So we're trying to get the common fraction, right? One fraction in the numerator. So let's do that. Let's make one fraction in the numerator. So you get x plus h times x plus y squared minus x plus h plus y squared all over the LCD, which is this, all divided by h. Now this is the area where you want to try to discover if you can distribute and kind of make this numerator here look a lot simpler than it is. Okay, so let's go ahead and distribute and simplify this particular numerator here. Okay, so let's do that. So we get the numerator becomes x squared plus xy squared plus xh plus yh squared. I'm sorry, that would be a little typo there. Plus hy squared minus x squared minus xh minus xy squared. So you see you do have some cancellations here. Y squared goes away, x squared goes away, xh goes away. So really you're only left with y squared h in the numerator. So it's a very big simplification. And then when you divide y squared h, when this is y squared h, you divide that by h, because h is non-zero, you just get plainly y squared on the numerator. So this just becomes limit as h goes to 0 of y squared divided by x plus h plus y squared, x plus y squared. And h goes to 0, so now we can put in h as 0, and that will become our partial. Okay, so that's our partial with respect to x. Of course, you can use quotient rule, but our particular question here was to specifically use the limit definition to compute the derivative. So we couldn't just go ahead and use our normal quotient rule, although we would love to because it would be much faster. So let's compute the fy, this first partial with respect to y of the same problem, and it's very similar. The definition is slightly different, but it's very similar to what we have going on in the last. Okay, so let's try to compute that. So we get x over x plus y plus h quantity squared minus this. Okay, and the LCD there is going to be x plus y squared times x plus quantity y plus h squared. So let's just get a common fraction, the same method as the last problem. So we got x plus y squared minus x x plus y plus h quantity squared all over our common denominator all over h. Okay, and I'm gonna pull the same exact trick where I'm going to try to simplify the numerator as much as I can before placing it back in to the problem. So let's look at that. So you get x squared plus xy squared minus x squared minus x times y plus h quantity squared. Immediately you notice that you can eliminate the x squareds from this expression. And we need to multiply out this other part here and distribute the x. So let's multiply it out. And distribute the x. And you notice that the xy squareds are also eliminated here, okay? And our fraction becomes much simpler. We're dividing by h, so actually we can take out one factor of h here, 2xy minus xh all over x plus y squared, x plus y quantity plus h squared. And here we can finally let h be 0. So when you do that, you get negative 2xy all over x plus y squared quantity squared. And that would be the first partial with respect to y using the limit definition of the partial derivative. If a question asks you to, please remember, if a question asks you to use a partial derivative in terms of the definition, please do so using the limit definition.